Hi, everyone. Thank you so much for joining this webinar. I'm excited to present to you some of the latest things that we have thought of for our vinyl community, but not only for our vinyl community. So Deborah was so nice to already read the title to you. So we're talking about like how we can expand the characterization capabilities with PVC building product formulations. And yeah, obviously, as you know, and most importantly, Brabender is now part of Anton, Paar, but all your beloved instruments are now in very good hands of like an amazing company that takes very good care of their customers. So we are all very thrilled that we have our new owners and that they are so devoted to all of you, our customers, and of course our colleagues. So this is just as a nice intro. Obviously, that is me, and this is Scott. Deborah gave already a nice introduction. So here's what we're going to talk about. So we have a lot for you guys prepared. There's a lot of data, but we upgraded some of our torque rheometer systems, but this is just some snapshot that you see from a slot capillary dye for extrusion capillary rheometry to color measurement, but also to some mixing studies and what matters. So here's the outline for our webinar. We have our motivation. Why are we doing this? The challenges that typically are faced by that. The instruments used, the measuring concepts and the results. And we have a conclusion and an outlook. Why are we doing this? So there's a whole lot of torque rheometers in the market with a lot of attachments to it. And since decades, there's a standard test method for the PVC vinyl formulation, which is ASTM D2538, to test the fusion measurement. But there's more that you can do because PVC is a unique material, especially the rigid one, that sometimes would benefit or most likely benefit from other principles of like characterizing the formulations. So we wanted to, since vinyl becomes more and more a fashion object when it especially goes to the exterior or interior of a house, the optical appearance plays a huge role. At the same time, environmental restrictions govern us in order to like make sure that there's a specific amount of recycled either pre or post-consumer content in our products. So in this case, I expanded the scope of this presentation to having two virgin window formulations and one set of data that has a virgin window formulation and two post-consumer recycled formulations added to it as well. You will see. And then obviously we want to make sure that you in the research community or also in the production controlling community have abilities to understand what your material is doing and hopefully save time and with that cost. Well, PVC is also unfortunately challenging. As it has many wonderful benefits, it also comes with some added baggage like degradability under too much shear and too much heat over too much time. So we have to make sure that we keep this in check. The mixer test in itself, because we're not talking about an absolute rheometer, is inherently prone to repeatability and reproducibility concerns. This is where my vinyl friends know me the best from like a couple of presentations, how we can identify, attack, and ideally, stop some of the major influencers or narrow it down for like a higher reproducibility and repeatability within the same equipment group. Yeah, the color comparison is, it is very, you can put numbers to it with color measurement. I will go over that, but it is also, it always depends on the lighting, on the mood, And there's also a psychological component to like the perception of color. Of course, we try to make this as scientifically accurate as possible, but still, not everyone looking at something will have the same color perception because it is so highly, biased by the user. The fine-tuning of parameters, this is always an ongoing challenge, trying to find like, what did we do to the material to get what data, and making sense of all of that. But if there is like one thing that I want you guys to take away with, and this is closest to my heart, make sure you understand the equipment and that you understand its capabilities, its limitations, but you can make the most out of it if you understand those guidelines. Instruments, here we go. The stuff that you love the most. So I split this up in 3 parts to make this easier digestible because we have an hour packed full of data. So everything that drives our world will be our latest generation, the Metastation 8E torque rheometer. We have then in the first part for the mixer tests, the Type 6 mixer from CW Brabender is a 3-piece mixer. We use roller blades. We have various different options that I will present in one trial for the loading, that you understand the differences there. And we have specific conditions for like typical rigid PVC formulations. Excuse me. The second part is the counter-rotating conical twin screw. We use this in 2 different ways. One is with a star-fed setup with a loss in weight. The other one is using a screw feed hopper to jam it up. And we use an inline slot capillary die. This is in accordance to like the extrusion rheology for ASTM D5422. And yeah, this is going to give us like viscosity out of the extrusion process and how it differs from like the typical standalone high pressure capillary rheometers. And then the third part is the color measurement part, where we use an external handheld device, consumer grade, for analyzing the color samples that we created with the first set of material data, first trials. I also have a couple of pictures of like the recycling ones. All right. For you to understand the torque rheometer, because a lot of people might struggle with like the concept, how do we actually measure what is the resistance? You all have to understand our torque rheometer has a pretty substantial motor. Here in this version, it's an 8 kilowatt motor that can deliver 400 Newton meters of torque at 200 RPM speed. We measure the torque by lever arm. So our whole motor inside sits on a pendulum. It can swing freely. We attach to the motor housing a lever arm. We attach a capacitive load cell, which you see here on the right side. So as the material in the extruder attachment or mixer attachment is being like giving resistance to the motor to spin freely, the motor wants to jerk around its own axis, and that translated with the lever arm gives you the force. The force applied, or the change in capacity of that load cell that you see here, is inversely proportional to the force applied. Force times lever arm, there's your torque. Key advantage here, we have a very accurate system from like 0.1 Newton meters all the way up to 400 Newton meters, which is just so if people don't understand how much 400 Newton meters are, if you have your beautiful 21-inch rims on your car and you have those bolts to tighten them down, they are typically applied with 110 Newton meters of torque based on the toughness of the bolt. So just if you quadruple that, that is what this motor delivers in order to mix material, for example. So it's a pretty beast. We have our mixing measuring head. Generations have passed, but still an all-time favorite. There's multiple versions. This can be part of an entire discussion for a webinar, but I just wanted to make sure that you get the majority of that. This is all. So as you can tell, there are rollers inside. The rollers blend the material. They're tangential. They're not intermeshing. And as the material melts and the PVC material starts to fuse, you will see, like, after the first loading peak, a secondary one, but I will get to that when we talk a little bit more about ASTM D2538. The differences that exist, they are for our legacy equipment and as well, of course, for our new generations of meta stations. And there's also international versions available. I will get more in depth when we talk about the key differences. Our conical twin screw extruder, also a long time favorite. It is quite compact. We have a whole bunch of different screws. The concept here is that the material is gently, and I pronounce this again, gently conveyed, because a rigid PVC is a shear sensitive mass. If you over shear it and overdo it, you will degrade it. So here you can increase the pressure by of course, the conical shape getting towards skinnier towards the end. With that, you reduce the volume of each flight and you increase the pressure. This is how you compress it. It has functional zones, each different screw. You can have, of course, a vent, you can have liquid additives, and everything comes on a little stand for easier cleaning, because obviously a conical screw cannot be pulled forward. You have to pull the barrel forward. So the screw is fixed, attached to the gearbox. That's why we have this funky little card there. Some feeders, this is just for your reference, what is available. Typically, it's still a twin screw system. You run it best if it's still starved fed. In some formulations, depends on how stable they are, you can also use a vertical stuffer to ensure that you have a good flow. You can combine those together or run it on hopper. I encourage, of course, to go with a tandem solution, but I've seen it in the practice in the field that people are also happy with the stability of the test results by running it on hopper. That's what I'm doing with one of my recycled ones. This is the capillary dye set. I have two pictures here after we cleaned them. One was for the first material set and the other one is for the very high viscous ones. When I'm talking high viscous, I'm talking about like already generating very high pressures that would be past what the extruder and the pressure and the rupture disc can handle, and also what your material can handle. So we modified the dye in order to handle chlorinated PVCs or highly filled rigid formulations for any kind of pipe applications, where a standard geometry might lead you already into the realm of like degradation. And we still want to have like a decent flow. And then you see some of the results that would come from our latest software. And then here, the color handheld device, the spectral guide, and some reference materials for our first formulation that we're going to identify, the two window ones. Software, in case you have been a long time Braebender user for decades, we had like a software package, well-beloved WinMix and WinExt. In 2016, Braebender introduced already the MetaBridge concept, and ever since it has evolved into like a very nice version of the same, but a blast into the future, because you can utilize the software on multiple end user devices like an iPad or an Android tablet, as well as, of course, the touchscreen that is built into the data acquisition system of the meta stations, all of them. And so from equipment setup to like the plotter graph to like the evaluation, everything is built in directly where you need it at your fingertips. You switch between the mixer and the extruder software based on the attachment that you have, but both are installed. Good. So you already got through like the equipment that we use. Let's go to the measuring concepts and the parts. Part one is everything mixer. So that's what I mean by like two different formulations. I have a trial A and trial B. The trial A data is the one with two rigid PVC window formulations that we did in the past. So we run it in 180 degrees, 60 RPM, 75% fill with a quick loading chute. The mixer is identical. Both are three-piece mixers, electric. They heated, latest generation from CWB. The trial B, we have one rigid virgin control formulation and two post-consumer recycled PVC formulations. What I did, we did mixer tests with fusion curves, like everyone would do with 2538. Then we have the loading system influence, where I want to show you how crazy it looks when you change something. Then extrusion comparison data. This is coming then later when we have part two with the extruder, including the rheological data and the color and gloss analysis. All right. This is the graph that everyone knows. This comes directly from the standard, but also from like the instruction manual. PVC acts and behaves like it's fairly unique in the thermoplastic world. So because of its morphology and the way that you can tailor make it based with like additives, plasticizers, and other stabilizers, waxes, each formulation is unique, but what has rigid formulations which joins them all together is the profile that you have. The material is going to melt. There's this like it's fully melted mass at B, and then at a specific onset point that we call the inflection point, we have like where the fusion speed is at its maximum. The material changes its morphology and it builds molecular weight, and with that it is going to have a secondary peak, the so-called fusion peak. The time between those two peaks, A and X, is the so-called fusion time. And at the end, you have like a specific, torque that was needed. Why are we doing this? You want to make sure that if you ever have a formulation that you want to then bring into an extruder to make a profile like a deck board, you want to make sure that you are not in the zone where the material does internal changes. You don't want to be between A and X. You want to be like past the X point to closer towards a stable version when you exit the die, because the last thing that you want is internal changes of the material when you're trying to give it its final shape, form, and stability. So that's why, but it is also incredibly powerful for formulation development because you can move that point X now almost like a target or a crosshair, left, right, up, down, based on the additives that you add. So this was the two window formulations, and here you can already see distinctive differences. One has a pretty distinctive fusion point, but it has like the infamous double hump, while the other one has like a not so distinctive one with a just a slightly later fusion point. But this is again based on like what the additives are. Our software allows the customers to select automatically if you want the first or the secondary peak if you have a double hump to be selected. This was customer feedback because it's more like a religious question. Some folks want to have it like when all of the material is fused, they pick the secondary one. Others like to see when do I have my first peak. Yeah. Here's just a comparison between the two of them. So as I already summarized, there was a defined fusion peak in the first one, even though it had the double hump. The second material had a lower fusion peak, less torque, and was not as defined. So what is also important, most of you guys know, but if you don't, the area under the torque curve is the energy consumed. And what that means, if you have, for example, you take the integral between A and B, and this is the total energy, mechanical energy that you put under those conditions there. So if you have your sample weight of, say, 63 grams for our 60 cc mixer in there, you can actually say, what is my specific energy, which you see here on the right. It is like 1,389, so almost 1,400 kilojoules per kilogram. The other one was only 1,360 kilojoules per kilogram. So this is something very nice and handy in order to like later scale for your like larger extrusion applications where specific mechanical energy becomes like a key scaling factor. All right, we had this. So this is now, you see, in our new software, we have the ability to, I mean, the old one had this as well, but to have like an average reference curve directly uploaded towards the graph. So you see here the yellow dotted line is the reference curve of the virgin material, while obviously the blue line is then the first recycled post-consumer rigid PVC formulation. This was a 50-50 blend, so it's a blend between virgin and post-consumer one. So you have like a very nice, distinct, but higher torque than the pure virgin. This typically post-consumer recycled content can have quite a substantial amount of like reinforcing additives in it, and maybe not everything. It generates more heat and with that a higher fusion. So now let's see how it is with the other formulation. The other one was even faster, slightly higher, again towards this reference, but you see even shorter fused. And we just realized that both recycled post-consumer formulations have a shorter fusing time than the virgin, because most of the material was already fused at one point. You know, this was already a final product. It was a window frame that just got into the shredder. So, pretty much like what I mentioned regarding like the analysis. We have like our two different formulations behave slightly different with a shorter fusion time for the secondary one, and with a similar level of specific energy, and both are higher energy, higher specific energy, and higher shorter fusion time than the other ones, than the reference material. All right. So influence on fusion test repeatability. So there's a reason why operator is number one, because most of the times it's your operator. But if it's not the operator and you have like the superstar of torque rheometry testing and of the, doing the Brabender test over and over again for like decades, then other factors that are substantial in the influence play a role as well. So we have the loading system. I will get into the loading system with some graphs. We have the gear ratio, blade geometry, the heat in general, electric versus liquid feed, heated mixer, PID parameters if you have an electric ones, the heater location, and the fill ratio. So let's get one by one. Again, the loading system, I will get into this, but with gear ratio. So there is, as you know, two different worlds of how there is a gear ratio difference. There's like the rest of the world with a type 5, where the driven blade is faster than the one that is attached to the torque rheometer. And then there's the other way around, where the one that is attached directly to the powertrain is the faster one. If you look in front of it, it's the left one, and then the other one is slower. So we already adapted ASTM D2538. All of those things, everything that you see here, except for the operator, you should mention in your test report and say, what did you use? And again, if nothing else from this webinar, please always mention, make this your takeaway. Make sure that you mention, what did you use? Did I use a type 5 or type 6 mixer? Different gear ratios. which blade geometry did I use? Did I use like the international Brabender mixer with like a displacement of with a free volume of 55 cubic centimeters, or did I use like the American version, the CW Brabender mixer that has 60 cc free volume in the mixer? Then of course electrically or liquid heated is obvious, yeah, the fill ratio, the ASTM standard D2538 is unfortunately not very precise here. They give like 3 different ranges of how high you can fill your mixer for great results, for great repeatability. And even Brabender says between 70 and 75. I pretty much constantly use 75 because I have the right fill. If you need more information, we have a wonderful presentation about finding the right fill, but this was just too much time to fit it here into my presentation. But here, let's go to the influence on fusion test repeatability just from the loading system. I did 3 tests with the virgin reference material of the recycled material, right? I mean, the reference there. So the first one is the so-called pneumatic load chute. The pneumatic load chute has like a piston where you just press 2 buttons and the pneumatic cylinder presses the material into the system without any operator bias. You know, the only operator bias is if the customer is too slow to like fill the hopper. But then the second one, we have something called the quick loading chute. The quick loading chute has a weight in the piston and like a little chute. And here I just, I did not push the material in. What I did, and what you see here, I just filled in the material, put in the 5 kilogram weight on top and just let go and just was amazed. So you see it took forever for it to like get into the mixer. Once it was in the mixer, it melted, gave us a teeny tiny loading peak, then gave us somehow similar-ish melt viscosity or melt torque. Had of course a significantly slower fusion speed and reached like the fusion point at the 2-minute 33-second mark, while the other ones reached that same thing at like 150, so like a minute and 30 seconds faster. Interestingly enough, since it took forever to get there, actually the fusion times are not that far off. We're talking like 15 seconds. But again, the exposure to heat, what you see here, is also completely different. So why am I having this slide? I just wanted to create awareness. Please standardize within your organization what you use. Our recommendation, what a lot of companies adopted, is to take the operator as good as it out of the equation and go with a pneumatic load chute that you can attach to the mixer, and you can just press 2 buttons. No matter how strong you are, how tall you are, you will always have the same. The third one, by the way, this is me running the mixer with the same quick loading chute as number 2, but I press as hard as I can without breaking anything the material into the bowl, and you see 1 and 3 are almost identical. So, but again, this one here is me 15 years of experience doing mixer tests. But if you have someone new, this will not, even with pressing down, it will not look like that. Anyways, so again, this is the influence of the loading system. All right, part 2, extruder. What we did, again, whenever you see here in the top header trial A, this is my 2-window formulations, right? So obviously we had to increase the speed by specific increments because we are now having the extruder setup that has the slot capillary die attached to it. And we obviously then want to look at like what is the pressure in the slot capillary die. I will get to that a little later, just so that you see like the differences between like our 2 formulations. Interestingly enough, you want to have the pressure as stable as possible, and you can see that here pressure 2, the pink line, is pretty nervous, which is not the best for getting good data, but at least the pressure 3, those are the 2 major pressure transducers that matter for the viscosity to get the wall shear stress out of your die. I will get into this in a little bit, but here you can see the plots. We compared them, of course. And then material one was less steady. And we were struggling there with the powder feed because all of this nervousness is pretty much a reflection on like how to feed the system. And even though I had a loss in weight feeder, it was, the material still gave me quite a substantial amount of like plus or minus. That's why with the second material, with trial B data, I used the stuffer and filled it up as good as I can and matched the speeds. And I had fairly nice results regarding stability of pressure, you will see. Material 2 was a little bit better, but the pressure was, as you can tell, the formulation 1 in red had a lower pressure ceiling than material number 2. Material 2 was higher filled. Here's the trial B. This is exactly what I was talking about. Here we use our vertical stuffer. It's a stuffing screw. So imagine you have like just an auger that is just pushing the material down into the conical twin screw. So we have in a flood fed situation, whatever the material is needed, you have excess material that is being forced into the screws to have like ideally always the same fill. You see, I did the same thing. I did like, in this case, I had like 40, no, my speeds were also 20, 40, 60. I was a little bit more aggressive with this one because I was able to handle it. But you can tell the blue curve is always the torque curve, the dark blue. And then we have like the pressure curves that you have to look for, are like the teal one and the purple one. So teal and purple are the ones that matter. And you can tell, especially here, if we look at this, this is 1 is the virgin, right? This here is the virgin. This here is the 50-50 blend, virgin plus post-consumer recycled, and this is a pure recycled content. So I love the one in the middle, which is extremely smooth. This one's very well, and it's like a really nice finish as well. While the other one at higher speeds, you see you have like a pretty decent one at like lower shear rates and lower RPMs. And then it gets a little cranky, and it gets a little nervous when you look at the torque curve, how it starts to jitter, because it cannot hold up with this under too high speeds and too high stress. And you will see this later in the viscosity results. But yeah, this is a very nice way of also characterizing the quality of your blend, because again, for like establishing the viscosity calculation, you have to make sure that those values are not on an upstream or downstream when you take the measurement, because otherwise you're all over the landscape. I will show you later why. So the rheological concept, I think most people have already realized that, but different fluids or different materials behave differently when you stress them, or when you shear them in this case. So there's a Newtonian fluid, which would be like water. So no matter how much you shear it, the viscosity doesn't really change. It's linear. If you have, that's what they call the Newtonian fluid, we have a pseudoplastic or shear thinning behavior. If as you increase the shear, actually the viscosity drops. The opposite, the dilatant, is like the higher the shear, the tougher the material gets. And we have like the Bingham plastic as well. There's another plot that is sometimes used. This is like the viscosity plot. This is the wall shear stress over shear rate. Just memorize that the pseudoplastic here in the second plot is like going up, while this is like going down, because later when you see the viscosity curves, you will see that. The formulations are like well established, but I wanted to show you here exactly. So you see, you make the translation. Those are our two window formulations, right? Remember, window formulation 1 was softer, window formulation 2 was higher filled. So what our system does, it takes obviously the delta in pressure, the two pressure graphs that I showed you. And from those two delta in pressure, you get like your wall shear stress. And the shear rate we estimate by taking the volume flow. And since we have the melt density of the material was 1.38 grams per cubic centimeters, we can calculate with the mass flow the volume flow. If we have that, we can directly correlate this to the shear rate. So we have, and if you have wall shear stress divided by shear rate is your viscosity. So we can, our system, give you different approximations so that you have like also that you don't need to do like a million tests. You can only do like 2, 3, or 4 points on the curve. And then this little calculator here in the top, if I would be live, you can actually type in whatever shear rate you want to have. And it's going to like tell you where it is defined, what then the wall shear stress and the viscosity would look like. So it's all built in. This is like a graph of the older version of our legacy software with Next, but in the new version of the MetaBridge, it works the same way. So again, here the plot. Oh, by the way, this is also fairly common and documented. There's like a so-called Rabinovich correction, which brings it from an apparent viscosity to a true viscosity. Rabinovich is typically a little lower, depending on like the material characteristic. It's a logarithmic fit for like getting the viscosity profile from that capillary into the realm where you need to be. So that's why we plotted both the uncorrected dotted lines. Here again, wall shear stress like this and viscosity like this. Our approximations can be selected. In this case, we use Caro. Caro was a mathematician that was also using different equations for the fit that is defined in the origin. As you can tell, my recommendation, if you have a slot capillary that is tailored in the shear ranges for extrusion, for profile extrusion, then use the Caro equation for the fit because it is defined closer to the origin. If you have injection molding applications where you need a very high shear range, then I would recommend where you like here in the 10,000s of reciprocal seconds, use the power law in order to like have, the higher ones, covered. Yeah, so here the two graphs, and I will compare them later. So here you can tell, remember I said formulation 1 was softer. So now you have it here also from the viscosity directly. In the same shear range, you have a significantly higher viscosity than the other one does. And here is like the correlation between the two. Don't get confused. Here you have to like take blue against red, blue against red. So this curve is the viscosity curve from material number 2. This one is the viscosity curve of material number 1. This is the shear rate. So I pretty much explained everything that is here on this rheological analysis. But again, it is very nice how clearly you can differentiate the formulations directly out of the extrusion process. And what I cannot emphasize enough, this is the reality that your material has seen. So if you are a die designer, you have to use this in order to make sure that when you cut the window profile die, that you get like the right viscosities and the right shear rates directly out of the history that the material had. Because especially because of the fusion behavior of PVC, you cannot just simply take an unfused powder and put it in a high pressure capillary rheometer and just, shove it through. It doesn't work like that. So you need to like fuse the material because its viscosity changes dramatically. Here's the rheological data from the second one. This is just the reference material. So we are like in a similar realm from the viscosity like the other window formulations. I just have like, it's not as curvy, but what is here also, the new version of our meta bridge showcases the same table, but you have it also like here, in this case, it takes the power law with the exponents and viscosity and shear rate. And here you see in the same scale, our viscosity is lower from like the, from our 50-50 blend. And this is, of course, explainable since we have less fusible material and more like so-called pre-fused, already done fused filler material. This can add, in my fusion curve was a shorter fusion time, but viscosity, you might have more slip. And here the other one was a little higher, so my 50-50 blend, but this directly can also be then correlated to our extrusion data where you see like the pressure values of that. But for us, what is important with post-consumer recycling, this method might give you a better indication of how the material flows in your extruder than the mixer test does. Because you saw from the mixer test, we had like very distinctive curves, but the viscosity does not immediately line up to that. So yeah, that's why it is such a powerful combination that you have both. The best part about it, if you have a conical twin screw already, you just, instead of having just a film die or sheet die in order to look at the optical properties for like, how does it look? You can do both and have viscosity data and optical properties. So that would be my recommendation. If you don't have one, you should get one. So last but not least, let's get to the measuring concept of the optical stuff. So now this is a little bit more generic for you to understand how we perceive color. So obviously color is the chemistry of like the surface and how we as an observer perceive the reflection of that when a light source hits that. This little device that we used has two different modes where you have like a light source that comes at a specific angle and the viewer is like in a specific spot. This is this 45-0 reflective method. There's everything there is also standardized. There's like a whole bunch of standards for that because again, it is part of like the dashboard of a car. You know, those handheld instruments are critical for consumer reception, whether or not it looks faded or fresh or nice. And then there's like also the so-called diffuse scattering method, where you have like a light source that is like omnipotent everywhere, and then you have the detector 8 degrees away from it. So I did both. But most of the modes that I used were the 45-0 reflective. For you to understand how haze and how gloss works, because we also want to know like how glossy is the surface finish. So obviously the first two are the ones that I just showed, but just for you to understand the diffuse scattering, and you see like how this whole magnitude of like what comes to you is called what is like from the gloss measuring, and the haze is like with this graphic they try to explain like how clouded it would be, so to speak. So this is just again for you a visual reference, like what we as an eye perceive of the surfaces. And again, vinyl products in the building sector have become more and more fashion objects like Gucci bags or, other items that are where color matters, because people don't pick the color they don't pick their vinyl siding based on like what's the best vinyl siding. They pick it on what's the prettiest and probably has the best price. As you can tell, the sunlight has a specific wavelength spectrum, our visible light between like the wavelength of like, what is it, 380 all the way to like close to 800 nanometers. There's like a halogen light, which is this F2, and there's like a specific direct LED light where you can scale this pretty accurately. So those are the two other ones. So you can see what would be the light spectrum of the sun, and then of like different light sources. And we want to make sure that we have this as uniform as possible to get like the best reflective. And then obviously when something is perceived red, you have it in a higher wavelength. If it is like green, it's more in the middle of the visible light, and bluish is towards like the lower wavelengths. Lassie has a concept created for like how can you measure this? How can you somehow put this very objective stuff, make it subjective, make it objective? So it works with reference materials. So you have a standard. This one picture that it had is a color standard. And what you measure is the difference between those standards. So we have a blue, we have a yellow, green, red. And based on like how far off you are, you can have a specific color perception, and you can put this into like the diagram. Then we have a so-called light index, which is like how light it is, or like how reflective. Sorry, that was one too fast. Careful with this. There's a standard where you have like the delta in all of those. If you add them together and you square them up and take the square root, and you have like a complete index, it could be, and look at this picture here, that a sample, for example, has identical colors, and every single thing is like 0.75, 0.75, 0.75, and the delta E is 1, while you have like 1 where you just have like that one color is changing dramatically while the others did not, and is also 1. You can clearly say they are different colors, but according to this method, it's not. It's the same. But again, this is a mathematical thing, just that you have an attention that, when you just see like specific values by that, this is just something to visualize that you have to be careful when you do this. So this is what I did with our window profiles. So G is the gloss. This is the gloss reference. This is always the standard. And here I just looked at the samples when they came out of the extruder, out of the slot capillary die, at different speeds here, 20, 30, 40 RPM, and saw what was the difference to the standards. So we had like from the lightingness, it was fairly close. Gloss, it was very matte, it was very damp, it was not high gloss. My delta E was almost identical between the two of them. So this is all the first material. Remember the softer one, softer formulation. So the other one showed at least with like the gloss that the gloss was reduced as higher I went with shear, but also we had an increase in yellowness. Remember when I said B is yellow, right? You see B plus is yellow. So when you have like, so B minus would be on the left side. So B plus is on the right side, but it was actually probably our residence time was a little too long, so it reduced in yellowness in this case over the time. So the other one, I didn't have the instrument available for this one, so I did the good old, I put them on my wonderful hardwood floor and looked at it. But you can immediately tell this is like the recycled one, this is the virgin blend, and this is the pure recycled. You can tell by the color already. The higher the recycled content, the grayer it gets, but highly dependent on what was in the post-consumer recycling. But also from the glossiness, the secondary, the last one had a fairly high gloss, while the other was very matte. But this is again dependent on what was the formulation inside. But yeah, it would be interesting once I have access to my spectral analysis to like expand this with like also putting numbers to the objective or subjective, not objective. This is wrong. This is a subjective perception of that. All right. Conclusion for the material. As you can see, our instruments were able to characterize the two different data sets, the two window formulations and recycled formulations, quite distinctively with methods that are well established. We saw like lower viscosity with the first material. We had a defined fusion, slight delay, was probably more internal softeners or waxes inside of there, or more plasticizer. We had a higher loading peak for the second material one, but it was not as distinct. We had a higher shear rate, higher drop, and it was less yellow than material one, good gloss. And yeah, from the analysis, we had like a very nice picture of like the whole, how the two formulations compare together. What I have for the general concept, a lot of our industry friends have torque rheometers, and a lot of the torque rheometers have attachments, and there's a lot of folks that always do the same tests over and over. I wanted to highlight here, or like was hopefully able to show you guys how you can like get extra information that can be really powerful at your fingertips by adding the slot capillary high viscosity dye to like an extrusion setup, and how you can like put this into good correlation with your mixing bowl and fusion tests. We work always continuously at ASTM, at the D201507 subcommittee for vinyl plastics, to make sure that a lot of that information is also hopefully soon standard, so that you can like rely on like an independent, hopefully bias-free reference for that. And yeah, as an outlook, obviously we can do more than just vinyl, so please visit us at the Polyolefins conference. So if you want to do film too. And yeah, we're pretty much at the end of the presentation. I thank you very much for your attention, and I think Deborah has maybe some questions. I'm here for.
Thank you. Let's take some questions from the chat window. The first question: are most PVC compounds processed or extruded at shear rates below 1,000?
Well, you cannot generalize that, but typically I've seen window profiles, and I've seen the higher the complexity, the higher the shear rate gets. But you have to like modify your formulation for that. But if you have a standard, if you just have a massive deck board, yes, it would be lower. But you know, the companies that make those different formulations, obviously they tailor make it for the application, because you can extrude the pipe, but you can also injection mold the fittings. So you will see if you go to Home Depot that you have straight pipe, which is extruded in a low shear rate, but the same exact formulation has to withstand the higher shear rates for like the fitting injection molding process. So yes and no, it really depends, but typically I would say if you just have a straight profile with with very limited complexity, you will be in a lower shear range. Yes.
Next question: any tips for consistent data when using the loading chute with weight and pushing?
Yeah, as fast as possible, ideally with the same, you want to expose the material to the heat inside the chamber, ideally at the same time. Of course, this is not possible because you have a specific speed that the rotors turn. But yeah, we push. But 2017, I did a test. I had like an operator that is 5'2" from the Philippines, and I have someone that is 6'4" from Poland, and try to have them do this, because obviously angle of attack matters too, and they got different results. So if you have operators of different height and you want to push, give them maybe a step stool. So, but Or like I said, maybe if you have end of year money, maybe invest in the pneumatic one because it takes all of that out of the equation. You don't need to worry about how strong or how tall a person is, but get it as in there, get it as quick in the bowl as possible.
Next question, can the slot capillary dye be used to evaluate external lubrication slip characteristics of flex PVC?
I have typically focused everything on my rigid friends. I I would tentatively say yes, but I would ask the customer to please contact us and send us samples or maybe visit us because I would love to like test this because we are currently in a project of like evaluating how we can like maybe predict any kind of obstacles that happen in the production process directly out of a slot capillary dye. So, and especially slip effects or like any kind of buildup effects would be lovely to see and analyze. But yeah, here I can only encourage to utilize the facilities that Anton Paar just built in Ashland. Visit us or send samples in. We would love to test this for you.
Next question, how do you manage the dye melt temperature when using the capillary dye with varying screw speed? Won't the temperature increase when increasing feed rate?
Um, Well, we have a pretty substantial mass of steel that is inherently very sluggish in reactivity. Also, you have to understand the dye is heated up to 180 degrees centigrade. Typically, you in your laboratory have 70 degrees Fahrenheit or 25 degrees centigrade, depends on your location. There's a pretty huge delta of T between the two of them. So we do optimize with the PID parameters the dye so that it does not overheat. But you can tell we have a stock temperature probe that also shows you if you have more heat coming from like more shear from the extruder side, how that relates. And there are in the slot capillary world or in the viscosity world, there's the so-called Oswald-de temperature shifts. So if you realize that you have a consistent shift of something based on like 2 or 3 degrees more centigrade on the scale, you can also mathematically get that out of there. But I haven't seen it yet because again, it's a massive boat anchor of steel that has a temperature, and in order for you to change that, it has to be really much harder, and then you have much other problems than a little bit of deviation in your viscosity curve because your thing will burn.
Okay, next question. How does the new generation of torque rheometers differ from the legacy CDW IntelliTorque and ATR torque rheometer systems?
Oh, yeah. So what they did, thank God, the German development team, they took a lot of the cues from the IntelliTorque generations with everything built into one device and made this the international global version. It has a more powerful motor in most editions because I guess my German colleagues, they love more oomph. But besides that, from like a sticker to sticker comparison, it, the core difference is that the data acquisition system with the new software is built in on a touch screen, while before that it was externally. And otherwise, all of the equipment, it is very similar to like the IntelliTorque ATRs, just with a more powerful motor and a couple of more heating zones. And again, the core difference is the touch screen with the software built in, and it's like, yeah, and safety features. Sorry, I forgot. So if you do need safety features like two-hand operation, safety switch, logout, tagout, all of that is available for the Meta stations as a standard, while the IntelliTorque needed that to be like retrofitted.
Next question. How do you optimize how much compound you can put in the bowl?
Oh yeah. So again, due to the time constraint, and I couldn't cover all of that, but we have a general guideline of like what is the bowl volume. Say every bowl from Brabant has 120 cubic centimeters without any blades. Then you put the blades in. The blades have a displacement. Every bowl geometry has a different displacement. So roller blades in the CW Brabant USA version have 60 cc displacement. So you take 120 minus 60 gives you a free volume If you would fill it with water and you would take a measuring cylinder, it's like, then you have 60 cc. Then you'd add the load factor or multiply the load factor. So you only want to fill it to like 75%, for example, because if you put it to 100%, based on the movement, the material would spill out. You don't want that. And then the last one is the melt density of your material. So PVC, rigid PVC is 1.38 grams per cubic centimeters. So we do this in our head, 60 times 1.38 or 1.39 grams per cubic centimeter. The centimeters go away, and then times 0.75. So with our CW Braben, a USA version, you have exactly 63 grams of rigid PVC that you would put in. In the international version, if you have the one from Brabener GmbH in Duisburg, Germany, you would fill 60 grams because their free volume is a little less. So, is a little more, no less. So, but yeah, what you can do is, and again, if you as a customer are interested, I made a wonderful presentation last Vinyl Tech about finding the right fill with some pictures that show how it looks like and what is the feedback. I would love to forward that. Just reach out. Deborah has all the contacts, or you have the contact information.
Next, are there different screw profiles available for your extruders? Can capillary rheometry be done on a single screw?
Yes, it can be done. And correct, it's good that we have so many different screw designs because we can simulate as close as possible what the production scale extruder would look like. But in general, it can be done on a single screw extruder. And we also have all different kinds of material available, but I would just strongly encourage to stick with a similar system to what your production uses, and the shear sensitivity does not go away. But I ran rigid PVC on a single screw. That's totally fine. You just have to have a gentle compression screw and yeah, not too crazy mixing in there.
Next question, when making formulation changes, what would be considered a significant difference in fusion torque between samples and the control?
Oh, already what I showed with my recycled one, but if you have like your gold standard formulation and you want to like change the the significance of change, well, I would say if you are like more than 15 seconds left or right of like fusion time, that can already make the difference whether or not you are like extruding too fast or too slow. Remember, you try to match your formulation that your extruder can optimize in the optimized process window. You need to figure out the speeds, the temperatures, and then make sure that your residence time is not too short, that you're like, because I guarantee you, your production guy is going to tell me, can I increase my speed? I want to make more money. And then you will tell him no, because the material needs to fuse. Or alternatively, you can fuse faster and extrude faster by more temperature adding it. But this is also a downside because you're riding the edge of degradation very closely. Because there's also something called shear degradation. And due to too much pressure and too much shear, the material can already start to degrade. And you will see this not immediately. And this was my key takeaway from last Vinyl Tech in October. Studies have shown that immediate changes in the shear were not immediately visible on like some of the color measurement, but later on in some weathering tests further down the line, because internally stuff changed, but it was externally not visible. That's why I'm encouraging to have all those three: mixer test, viscosity data, and color measurement, because from that you can get ideally the best in order to predict how your material will handle the non-stop demand of production to run faster, hotter, wider, whatever. It's just, yeah, that's as good as I can.
Okay, those are our questions. Do you have any final comments?
again, for the vinyl community, we are extremely happy to like be of service and to continue to evolve, and also make sure that on a standardization level, there's good data available, so that the confusion about like what should I do with my old data and what should I do with my existing equipment gets less. So the more we educate and the more we train, the better off a lot of the things are, because then the discussions gets less heated, which is what we hope we can serve you all with. So, and thank you all for your attention.